Hey everyone, and welcome back to the channel. Imagine for a moment that the universe, vast and unknowable as it often seems, still holds secrets so profound, so utterly disruptive to our understanding, that some might prefer them to remain just that, secrets. What if I told you that not merely a star or a planet, but an entire galaxy, a collection of hundreds of millions of suns, might have been intentionally overlooked, its true nature downplayed, perhaps even, dare I say, covered up by the very institutions dedicated to unveiling the cosmos? It sounds like science fiction, a cosmic conspiracy theory, but the truth, as it often is far stranger and infinitely more compelling than fiction. Today, we're diving into the astonishing story of a galaxy that shouldn't exist, a celestial anomaly so baffling it forced us to question everything we thought we knew about the universe, and why for a time, its existence seemed to challenge the very fabric of scientific consensus. Get ready, because what we're about to explore could rewrite the textbooks, and it all began with a faint, ghostly patch of light in the night sky. For decades, our cosmic understanding has been built upon a cornerstone: dark matter. This invisible, mysterious substance, we are told, makes up about 27% of the universe's mass energy content, far outweighing the ordinary matter that forms stars, planets, and us. Without dark matter, our models of galaxy formation simply fall apart. Galaxies wouldn't hold together, their stars would fly off into the void. It's the cosmic glue, the scaffolding upon which the universe builds its grand structures. This understanding is enshrined in the Lambda-CDM model, our prevailing cosmological framework, a triumph of modern astrophysics. So fundamental is dark matter that discovering a galaxy without it would be like finding a fish without water, or a fire that produces ice. It's an impossibility, a direct challenge to a century of scientific effort. And yet, tucked away in the constellation Cetus, a little over 60 million light-years away, there sits a galaxy that did just that. Its name is NGC 1052 d-F2O, or simply d-F2O. Initially, d-F2O didn't look like much. It was discovered during surveys of ultra-diffuse galaxies, UDGS, a relatively new class of objects that are as large as the Milky Way but contain only about 1% of its stars, spread out so thinly they are almost transparent. You could theoretically see distant galaxies right through their centers. d-F2O fit this description perfectly: a gigantic, ethereal wisps of stars, seemingly unremarkable, just another UDG among hundreds. For years, it floated in the catalogs, a ghost in the machine, not warranting much more than a footnote. But then, a team of astronomers led by Pieter van Dokkum at Yale University, using the Dragonfly telephoto array, began to look closer. They weren't just observing, they were measuring. And what their measurements revealed was not just an anomaly, but a cosmic impossibility. To understand d-F2's peculiarity, we need to talk about how we weigh a galaxy. You can't put it on a scale, of course. Instead, we measure the speeds at which its stars and globular clusters orbit its center. The faster they move, the more mass must be present to keep them gravitationally bound. In most galaxies, when you add up all the visible matter, the stars, gas, dust, it accounts for only a fraction of the gravitational pull needed to explain the orbital speeds. The rest, the overwhelming majority, is attributed to dark matter. It's the invisible hand guiding the cosmic dance. When Van Dokkum's team observed d-F2O, they focused on its bright, compact globular clusters, dense groupings of millions of stars that orbit the galaxy's core. These clusters are like little gravitational speedometers. What they found was astonishing. The globular clusters in d-F2O were moving at speeds consistent only with the mass of the visible stars. There was no extra gravitational tug, no hidden hand. The stars and clusters were moving as if dark matter simply wasn't there. This wasn't just a little bit of missing dark matter, it was all of it. d-F2O appeared to be a galaxy entirely devoid of dark matter. The implications were staggering. If dark matter is truly the universal scaffolding, how could an entire galaxy form and survive without it? This observation wasn't just a puzzle. It was a direct challenge to the very foundation of our cosmological model. And for a time, the scientific community's reaction was, shall we say, less than enthusiastic acceptance. There was a palpable sense of disbelief, a desire to explain away the data, to find a conventional loophole. This, my friends, is where the cover-up truly began, not a malicious conspiracy, but the natural, human, and institutional resistance to a paradigm-shattering truth. Scientists are, by nature, skeptics. Extraordinary claims require extraordinary evidence. The initial reaction was to scrutinize the methods. Were the distance measurements accurate? If d-F2O was actually much closer, its stars would appear fainter, implying less visible mass, thus making room for dark matter. But the team had used multiple independent methods to measure its distance, all converging on the same figure. Were the velocity measurements wrong? Perhaps the globular clusters were not true clusters, or their velocities were misinterpreted. Again, the team meticulously rechecked their data, bringing in independent groups to verify the findings. Each reevaluation only strengthened the original conclusion. The evidence was robust. DF2O truly seemed to be a galaxy without dark matter. The scientific literature of the time reflected this struggle. Papers were published attempting to find alternative explanations. Perhaps DF2O was a tidal dwarf galaxy, formed from the debris of a galactic collision, which might explain its lack of dark matter. Or maybe it was just a statistical fluke, an outlier that would eventually be explained away by more precise measurements. The prevailing thought, the established paradigm, was so strong that the immediate reaction was to contain the anomaly, to prevent it from truly destabilizing the dark matter consensus. It wasn't an active cover-up, in the sense of hiding evidence, but rather a collective, systemic attempt to fit the square peg of DF2O into the round hole of lambdictum. It was a scientific community struggling to process a truth that fundamentally altered its worldview. But Van Dockum and his team, along with other intrepid astronomers, refused to let DF2O be quietly dismissed. They continued their observations, gathering even more data, pushing the limits of their instruments. They used the Keck Observatory's OSIRIS spectrograph and the Hubble Space Telescope's Wide Field Camera 3, some of the most powerful eyes humanity has built to peer into the cosmos. Their subsequent papers became even more emphatic. The galaxy's mass-to-light ratio was incredibly low, consistent only with its visible matter. The missing dark matter wasn't just a possibility, it was an observed fact. And then, the universe, with its endless capacity for surprises, delivered another blow to the conventional wisdom. Not long after the initial findings on DF2O, another ultra-diffuse galaxy, NGC 1052 DF4, or simply DF4, was found in the same region of space, exhibiting the exact same characteristics. Another galaxy, seemingly devoid of dark matter. This wasn't a fluke, it was a pattern. Two dark matter-free galaxies existing in defiance of our understanding. The case was no longer ignorable. The cover-up, the quiet dismissal, the attempts to explain it away, could no longer hold. The truth of these galaxies, the fact of their peculiar existence, had broken through. So how did these galaxies form? How can they exist? The answers are still debated, but several fascinating theories have emerged. One idea is that DF2O and DF4 were somehow stripped of their dark matter. Perhaps they had a violent encounter with a much larger galaxy, and the dark matter halo, being more diffuse and spread out, was gravitationally torn away, leaving behind only the tightly bound stellar core. However, detailed simulations have shown that stripping dark matter so completely, while leaving the stellar components relatively undisturbed, is incredibly difficult to achieve. The timing and dynamics of such an event would need to be very precise. Another, perhaps more exotic, theory suggests that these galaxies formed under unique conditions where dark matter simply never accumulated. This would require specific local environments with unusual dark matter densities or very early formation scenarios that differ significantly from our standard models. It might even point towards modifications to our understanding of gravity itself, perhaps an alternative to dark matter like modified Newtonian dynamics, MOND. Though MOND typically struggles to explain observations at larger cosmic scales, the existence of DF2O and DF4 forces us to confront some of the deepest questions in cosmology. If dark matter isn't universally present in all galaxies, what does that mean for galaxy formation theories? Does it imply that dark matter and ordinary matter can decouple in ways we hadn't anticipated? Could there be different flavors of dark matter, or different conditions under which it interacts, or fails to interact, with baryonic matter? Moreover, these discoveries highlight the fascinating, often frustrating, but ultimately rewarding process of scientific discovery. The initial resistance to DF2O wasn't necessarily ill intent. It was the natural conservatism of a scientific community grappling with data that threatened to upend a successful and well-established paradigm. It's a reminder that even in science, there's a strong human element, a natural inclination to defend what is known against the unknown. But ultimately, the evidence speaks for itself. The persistent efforts of astronomers to meticulously gather and re-verify their data ensured that the true nature of DF2O and DF4 could not be ignored. The implications ripple across astrophysics. If there are galaxies without dark matter, could there also be regions of the universe where dark matter behaves differently or is distributed in unexpected ways? These ghostly galaxies, once dismissed as statistical anomalies, are now seen as cosmic laboratories, providing unique insights into the properties of dark matter and the very early universe. They are forcing us to refine our models, to be more flexible in our assumptions, and to be open to the possibility that the universe is even more diverse and complex than our current theories allow. The story of DF2O and DF4 is not just about a couple of strange galaxies. It's about the very frontier of our knowledge. It's about how sometimes the most revolutionary discoveries are the ones that initially seem impossible, the ones that they try to explain away, because accepting them means dismantling deeply held beliefs. It's a testament to the scientific method, where ultimately data, rigorously tested and verified, triumphs over preconceived notions. These galaxies are no longer covered up. They are now beacons, shining a light on the profound mysteries that still await us in the cosmos. They tell us that the universe is still full of surprises, and that our understanding is far from complete. What other cosmic truths are still out there, waiting for tenacious astronomers to pull back the veil, challenging everything we thought we knew about the universe? Thanks for watching. Please subscribe my YouTube channel for more interesting videos.